Yeah, my name is Youngmin Lee from Department of Chemical Engineering. So today I'm going to talk about network formation of thermal reversible epoxy and their application for reversible adhesive. So starting from the general introduction of my research topics and then go detail. And this work conducted intimate collaboration with two research groups, Dr. Chaudhry groups and Dr. McCoy group. And the first topic about network formation is done by my student Gan Kim. And the second work about reversible adhesive is done by Samantha Knight. And yeah, here's an acknowledgement for the funding support. Polymer recycle for circular economy is a big keyword in relevant research as well as the relevant industry. So far, polymeric recycle is done those three category methods. The first one is mechanical recycle. It's basically we chop out the polymer product and use that as a filler in the new different polymer composite system. So we just use as mechanical filler. Second one is energy recovery. So about the incineration, we burn it out and we collect their heat and use that for the generation for electrical power also. And third one is chemical recycling. So pyrolysis, gasification, depolymerization. So we try to recover the raw material. But all of these are processing approach with conventional non-reversible polymer. But as a researcher in the polymer chemistry and polymer physics, I want to do some molecular approach to develop reversible polymer inherently. Okay? So here we are using reversible network polymer and introduce that reversible group into the thermal set material, so inherently non-reversible material. Then we can make reversible network structure. So during polymerization, they form network structure from right-hand side to left-hand side, but under certain stimuli, so it could be heat, it could be light, or it could be pH change, then the reversible group dissociated, and then this network structure go back into the segment state. Then we can do additional steps. So recycle, self-healing, or reprocess, things like that. And my final goal in my research group is using this material as a 3D printing feedstock. And first we print and use it. After use it, end of their life, we can recover it. And by heat or light, we can get back to the 3D printing feedstock again and use it. Or that mechanism also work for the self-healing part. So we print a fine structure and some crack we got. We cannot do overall heating. Then we collapse their fine structure. Instead, we can make some light or some other specific method. We can specifically heal that crack and keep using that printed part also. And for the reversible network, I use Diels-Alder reaction. Diels-Alder reaction is using the diene. In our case, we use this furan group, 5-member heterogeneous ring. And dienophil, in our case, we use maleimide. So these two functional groups separated, but at room temperature or some low temperature, they reacted and form cycloadduct like this. And during this forward reaction, they form network structure. But when it heat up, they go into the reverse reaction. They separate back into the furan group and maleimide group, and we can get the segment state. Okay? And the good thing is this reaction, we don't need any extra stimuli like a pH change, or they don't associate with any byproduct like water. First work we done is we prove our concept So our material actually go into the transition from network state to the segment state. So this one is rheology data. So y-axis is viscoelastic modulus, x-axis temperature. So low temperature, they have high modulus, it's a strong material. And as heat up, so they pass through the glass transition. So now they molecular chains got mobility and they're softened. This black curve is a conventional epoxy, conventional non-reversible network. So they just got softened by glass transition transition, but there's no additional transition. So keep their permanent network structure. But in our material, we have additional transition that is due to the reverse Diels-Alder reaction due to their transition to the segment state. And actually, we can easily see, visually, we can check their transition. So it's a DMA run before and after. So they show a melt-like behavior. But I would not say melt because melt means a physical phase transition. But in our case, that transition is done by chemical bonding change. Okay? So chemical change. And also we prove concept by incorporating by nanoparticle. So we can do this transition by light as well as heat. Okay? Next one is during this project, we found some side reaction, loss of their recyclability. So initial state, we can observe some good transition from solid-like material to liquid-like material. But during this transition, at some point, they lost their transition and just got stuck into the solid state. So in this project, we identify that reaction is due to a certain side reaction. So our intention is furan group react with maleimide group. And when they detach this maleimide group back, react to the furan group. This is what we want. But once they got freed, maleimide group can react with another maleimide group. So then they form this type of another structure, but that structure is non-reversible. So gradually we lost their recyclability. Okay? And in this project, we use two approach. First, we include the radical inhibitor because this reaction initiated by radical mechanism. So we introduce the radical inhibitor, or we use some different structure of maleimide precursor. So by this, we can retard the onset of side reaction efficiently. So 20 to 30 degrees Celsius postpone. In time domain, we can retard twice or 3 times. So without anything, this side reaction onset is less than 10 minutes, but by adding radical inhibitor and use new maleimide precursor, we can retard their onset after 30 minutes. Okay? That is second project. Next one is about the reaction kinetic study. Actually, reaction kinetic study has been done, but most of them is in the diluted solution with the model compound. But the reaction kinetic in dilute solution not necessarily same in the bulk resin. So we want to use some approach. We can study their kinetic in bulk directly. Okay? So here, that's why we use some rheometry again. So that is rheometry again. But in this case, we study as a time domain instead of temperature domain. And there's some equation, Flory-Stockmeyer equation, to predict when this network structure appear. So here we measure two variables. One is G prime, is called storage modulus. Second one is a G double prime, so-called loss modulus. You can simply understand storage modulus represent their solid-like property. Loss modulus represent their liquid-like property. So at the beginning, it's resin, so like a viscous liquid. So that's why G double prime is greater than G prime. But as time goes, they start to form network. And once they form macroscopic network structure, then they got intersect. So this G prime go beyond over the G double prime. That means that is the moment our liquid-like resin turns into solid-like network structure. Okay, so we measure this time to take they form network structure, and we can predict the reaction conversion to make network structure by this equation. So by this data, we can study their reaction kinetic. Okay. And during that study, I got some simple question. So if you check this equation, this Fm or Ff is functionality per molecule. So if you increase the functionality per molecule, we got greater value in denominator. We can decrease the critical conversion. That means we can get network structure in early stage of reaction. Then, how much functionality we can increase and how far we can decrease this critical conversion. So for that, I want to increase extreme functionality and want to study their reaction kinetic. So to realize extreme functionality for the molecule, so I prepare microsphere. So that is simply we make aggregate of the precursor, and simply one molecule you can imagine is an angstrom scale or 1 nanometer-ish, but I made greater than micrometer scale microsphere. So there are numerous functional groups on the surface of microstructure. Okay? And we combine with molecular level small precursor, so here and here, and then we do the same the kinetic gelation study. Okay? And we can see by adding this microsphere, and we can see their gelation time decrease, but we add a certain level greater, the gelation time getting greater. So we thought that is due to some formation of aggregation. They cannot effectively participate in the network structure. And that is plot for the weight percent of microsphere and gelation time. So initially they decrease, but we add more, they increase back. We assume that is due to the formation of aggregation. And that is study for the identify how many functional groups they have in the microsphere. How many times I can use more? 1 more minute. Okay. Then just quickly move. Second topic is about reversible adhesive. So this one is use a debonding on demand reversible adhesive. That is, when they work, they can hold 2 parts strong, like a conventional adhesive, but under certain stimuli, as I said, it's like a heat or light or pH change, they can detach. Okay, but the problem so far is they have weak, strong adhesion strength. So maximum 7, but mostly 2. But conventional adhesive has even stronger, 10 to 20 megapascal. So we use our system and measure their adhesion strength. This one is a commercial one, Gorilla and JB World. It's 10, 20 megapascal strong and non-reversible. But ours are similar 10 to 20 megapascal adhesion strength at operation, but they can drop 0.1 megapascal level as a heat up. It's a debonding state. And they also show the reattachment 1 to 3 times. Okay. So that is summary. So we used reversible network structure, and first I studied their network formation behavior with addition of microsphere, so functional groups, numerous functional groups. And second, we use the same system for the reversible adhesive, and we can, by changing their molecular structure, we can effectively increase their adhesion strength at room temperature, and also we can see the on-off behavior. by heating up, we can effectively reduce their oxygen strength 10 times or 100 times lower. Yep. Thank you.